Hello and welcome to The Explainer. Today we're going to break down an absolutely groundbreaking paper from NVIDIA. It details a platform called Cosmos, which is basically a system designed to build a digital twin of our world, all for one reason: to teach AI about physics.
Okay, so let's just dive right in by tackling a fundamental challenge. We've got AI that can write poetry, that can create amazing art, but teaching a robot to do something as simple as loading a dishwasher, it's incredibly difficult. Why is that? Well, it's because the physical world is messy, it's unpredictable, and in the real world, actions have consequences. You see, training an AI in the real world is painfully slow. It's super expensive, and honestly, it can be pretty dangerous. A self-driving car can't just go out and practice crashing a million times to learn what not to do, right? The amount of data you can gather is limited by what you can physically and safely do. But what if an AI could practice first, in a totally safe, infinitely repeatable environment?
And that right there is the solution. It's this long sought-after idea in AI research to create a digital twin, a perfect virtual copy of reality. Think of it like a digital sandbox where an AI can go through millions of scenarios, make all the mistakes it needs to, and really learn the laws of physics, all without any real-world risk.
This kind of super simulator has a name. It's called a World Foundation Model, or WFM for short. You can think of it as a flight simulator, but for any AI that needs to interact with our physical world. And today, we're going to look at NVIDIA's incredible new platform for building these very models, Cosmos.
So how in the world do you actually build a digital twin of reality? It sounds like a monumental task, and it is. But the Cosmos platform breaks it down into a clear, scalable process.
The whole process really boils down to 3 key steps. First, you've got to feed the AI a massive visual diet of the world in action. Then, you have to figure out how to translate all that rich visual information into a compact, efficient language the AI can actually understand. And finally, you use that new language to train the model's brain, basically letting it discover the fundamental patterns of physics all on its own.
So let's start with the data, because the scale here is it's staggering. The Cosmos project kicked off with a library of 20 million hours of raw video. To put that in perspective, that's over 2,200 years of continuous footage if you tried to watch it all back to back. Just incredible.
Now, what's really interesting here is the diversity. This isn't just one kind of video. No way. To build a general understanding of physics, the AI needs to see everything. We're talking traffic patterns, robotic hands moving objects, people walking around, and even the dynamics of nature. This variety, that is the secret sauce.
Of course, you can't just dump 20 million hours of random internet video into an AI and hope for the best. Cosmos uses this really intelligent pipeline that chops up the videos into coherent scenes, filters out all the low-quality junk, and even uses another AI to write a description for each clip. So what's the result? About 100 million clean, diverse, high-quality video clips, all ready for training.
Okay, but even after you've curated all this amazing data, you run into another huge problem. Raw video files are enormous. They're computationally expensive. Trying to feed them directly to an AI would be wildly inefficient.
The answer is something called a video tokenizer. This is such a critical piece of the puzzle. You can think of it like a Rosetta Stone for video. It's a super advanced video compressor that learns how to turn all those raw pixels into a compact sequence of tokens. A brand new, highly efficient language that represents the visual world without losing the essential info about motion and physics. Now, this is where it gets really clever. Cosmos doesn't just create one type of language, it actually develops 2. One creates these continuous vector-based tokens. Think of these like a smooth, flowing watercolor description. They're perfect for capturing really subtle, nuanced details. The other type creates discrete, integer-based tokens. These are more like crisp, individual words, highly compact, and super efficient for the AI to process. And this whole 2-language approach is designed to feed 2 totally different kinds of AI brains. The diffusion models, which use those nuanced, continuous tokens, they're kind of like a sculptor who starts with a block of random noise and slowly chips away to reveal a clear, coherent video. Then you have the autoaggressive models. They use the efficient, discrete tokens and work more like building with Legos. They look at the pieces already there and predict the single best block to add next, one step at a time. And as you can probably guess, forging these 2 powerful AI brains on all that data required a staggering amount of computational firepower.
The entire pre-training process was done on a massive cluster of 10,000 NVIDIA H100 GPUs. But this colossal effort, it isn't just about raw power. It's about creating a foundational intelligence that developers everywhere can then build on top of.
And that right there brings us to the platform's true genius. Because look, building a giant, general-purpose model is only half the battle. The real magic is how it can be adapted.
So the result of all that data, all that tokenizing, and all that training is what we call a pre-trained world foundation model. This is a generalist AI. It hasn't been taught any one specific task, but it has this broad, foundational understanding of how the world works. You know, gravity, objects being solid, momentum, all that good stuff. So the crucial point here, and the paper says it perfectly, is that this pre-trained model provides a great foundation. Developers don't have to start from scratch, and that saves an immense amount of time and computational resources.
This is the core idea, and honestly, it's a total game changer. It basically democratizes the creation of really sophisticated physical AI. A developer can take this powerful generalist model, add a much smaller, specific dataset for their own unique problem, and then fine-tune it to create a highly capable specialist AI.
And you can see exactly how this works in practice. Let's just pause on this for a moment. For robotic manipulation, you feed the generalist model some video of a specific robot arm doing its thing. It then becomes a specialist that can accurately predict what's going to happen when that arm moves. Or think about autonomous driving. You give the model specific driving data and vehicle movements, and bam, it transforms into a world-class driving simulator that gets complex traffic dynamics. It's just an incredibly efficient and versatile approach.
So this brings us to the most exciting part. What does all this technology actually unlock? Where does this all lead?
The applications are, well, they're profound. Let's break these down. Policy evaluation means you can safely test an AI's decisions. For example, you could see how a delivery drone handles a sudden gust of wind 1,000 times without ever risking a real drone. Policy training goes even further. You can teach an AI entirely new skills. Imagine teaching a robot to assemble a new phone just by showing it simulations. No physical prototypes needed. With planning, the AI becomes a strategist, simulating thousands of possible futures to pick the best move, kind of like a chess grandmaster thinking 10 moves ahead. And finally, synthetic data generation. This creates this powerful feedback loop where the simulator can generate brand new, perfectly labeled training data to make other AIs even smarter.
So the ultimate takeaway is really this. Platforms like Cosmos are bridging the gap between the digital world and the physical world. By giving AI a safe place to practice, a place to learn and make mistakes, we dramatically speed up its journey to becoming a safe and effective partner in our world.
All of this makes a future with truly capable physical AI. Robots in our homes, in our factories, on our roads. It makes it feel not like some distant possibility, but like something that's much, much closer. And that leaves us with one final thought to chew on. If an AI can safely practice and master any physical task in a simulated world, what will it truly be capable of in ours?